focus a little bit on acceleration. And we're going to look at the same example we looked at last time when we were talking about displacement and velocity. Okay, so this is the function showing the displacement, and if basically the particle was moving left or right with this displacement function. So if I graph that first of all, here's the curve of this cubic equation. Okay, so here it's moving towards the right, but it's sort of slowing down, and then it changes direction and it starts coming back towards the left, and then it starts slowing down again, changes direction here, and then it moves towards the right. So if the rate of change of the distance over the time is the speed, the rate of change of the displacement over time is the velocity, and rate of change means it's the gradient or the derivative. Now, if I actually plot the derivative using GeoGebra, I don't have to work it out manually. I can just type S prime of t, and it will just calculate it for me and graph it. Now, the key thing, the thing that we discussed last time, was that if the velocity is positive, then it means that the particle is moving to the right or upwards. In this example, it's to the right. And if the velocity is negative, then the particle is moving left or upward or downwards if it was on an up-down axis. Okay, so in this case, we can see that although the derivative here is going down, you can still see that it is positive. In other words, the value of this here is always above the x-axis. Okay, so on my green graph, between here and here, the particle is moving towards the right, and you can see that on its corresponding points on the derivative function, all of those points on the derivative function are positive. They are above the x-axis. And then between here and here, the particle is moving left, and the velocity between here and here, between those corresponding points, is negative. Its negative velocity means it's moving left, and then a positive velocity means it's moving towards the right. Now, hopefully it's not too much of a stretch to say that if the rate of change of the displacement over the time is the velocity, then the rate at which the velocity is changing, the rate of change of the velocity over time, is the acceleration. So if you differentiate again, you've actually got a function for the acceleration. Now, if I plot the acceleration function, the key thing for the acceleration is if the acceleration is negative, in other words, here the acceleration is below the x-axis, so its value is negative, and it's negative until here. So that means that the velocity is decreasing, and you can see if we just look at the velocity here is decreasing. Okay, and then from this point on, the velocity is increasing, and this corresponding point on the acceleration curve is positive. So all along here, the acceleration is positive, and that means that the velocity is increasing. Now, let's see what that looks like with respect to what we had here. So basically, if the rate of change of the displacement over time is velocity, then what I was looking for here was the rate of change of the velocity over time is the acceleration. Okay, and this is like really important summary. This basically means that the acceleration with respect to time is the derivative of the velocity with respect to time, which is the second derivative of the displacement with respect to time. And if you wanted to expand on that, the velocity with respect to time is the first derivative of the displacement with respect to time. Okay, so if the acceleration is positive, then the velocity is increasing. If the acceleration is negative, then the velocity is decreasing. And if the acceleration is 0, then the velocity is just staying the same. The particle is moving, just moving at a constant speed. So let's run through